Hello. Okay. Any question from this time? So next week will be midterm, so this week we will not have homework. So we'll talk about this quantum universality, which is kind of interesting, but it's hard to have homework anyway. And okay. So anyway, so this time we start on this chapter of quantum universality, and we start with something that's not quite about universality, but more principles on quantum circuit model. So there are those 3 principles on quantum measurement. And the first one is that the measurement we do is always in computational basis. And then the actual first one is the principle of deferred measurement, where all the measurement can be pushed to the end of the circuit. Because if you do some adaptive thing that's controlled by your measurement result, you can just replace that by a controlled unitary. And then the next principle is the principle of implicit measurement. It says that at the end of your circuit, you can measure every qubit, even if your algorithm don't already require that. And this seems a little weird. Why is this useful? But we see that we already see that in the analysis of Simon's algorithm, that we can do this principle of implicit measurement and condition on the result of this extra measurement, and that actually made our analysis easier. Okay, so those are the 0, 1, 2 principles of measurements in the circuit model. Then we start doing the quantum universality, and then we introduce more concepts about quantum gate. So first is this concept of function basically matrices. Here, so we focus on matrices that are diagonalizable, and we define a function on diagonalizable matrices just by saying you apply the function onto the eigenvalues of your matrices. And we see that this makes a lot of sense, because then say your function is x squared, then that will just apply to your matrix will just equal to your matrix square. And more generally, if you apply your function to the Taylor expansion, then you just do the same Taylor expansion on your matrices. Okay, and yeah, we need to go to this form because the powers of matrices is the integer powers of the matrices are defined by, say, if you have a to 1.5, then it's something, then you don't really know what it is. But now, if you see a to 1.5, then you do Taylor expansion, and that's how it is defined. Okay, so that's that, and then we define those 3 quite physically motivated family of gate. So there are rotation on x-axis, rotation on y-axis, and rotation on z-axis. And even if we don't know the physics, we can just have the mathematical definition here. So there are exponentiates of the sigma x, the Pauli matrices, sigma x, sigma y, and sigma z, and to some angle theta. And there is about some over 2 totally because of physics reasons, but that's what it is. It's theta over 2, and we define it that way. is consistent with all the literature and consistent with the physics. And well, this definition can be interpreted with this Taylor expansion formula, and we see that it's very similar to this Euler's formula, cosine e to the I theta equal to cosine theta plus I sin theta. And here, this theta is more like theta x, so you have this cosine theta identity and as I sin theta, then you have sigma x, sigma y, and sigma z. And you write in matrix form is these functions. Okay, any questions so far? If not, then we start going into our very brief introduction of quantum universality. And so the first thing we want to do in universality is decomposing every single cubic unitary into rotations. And obviously there is symmetry, so which two axes you pick doesn't matter. But here we pick y and z. So we say, so just from physical intuition, we think any rotation on this block sphere can be decomposed to some rotation about the axis, then some rotation on y-axis, then some rotation on the axis. And there is complex number, so there is probably a global phase, and you can prove that with careful calculation. So here we see that you have A, B, C, D, and the details are here and also in the book, so you can check them. And so that's decomposing your any single cubic unitary into rotations. And this is actually setting up to other things. So we're actually setting up to 2 cubic unitary. And so let's go to jump a little ahead. So we are having that form actually because we want to set up for control unitary. So what we are doing is from this rotation decomposition, then we can get our single cubic unitary u into this weird decomposition. U equal to some e to the I alpha, just like u e to the I alpha both, then some rotation A and times sigma x times another rotation B times another sigma x times another rotation C, where now this ABC multiplies with identity. And you can see this is quite directly modified from our previous decomposition. So we say our unitary is decomposing into those 3 rotations, is RZ beta, RY gamma, and RZ delta. Then we just say A equal to this RZ, then RY, then divide by 2, and B is something weird. B is some RY negative and RZ with this angle, then C is rotation Z with this angle. Then when we multiply them together, then the rotations basically cancel them out. So this y negative rotation and y positive rotation will cancel out to identity. And this z negative rotation, z positive rotation, and z rotation, they all cancel out to identity. So we didn't quite say this, but you can check that if you have 2 rotations with the same angle. So remember the rotations are defined here. So if you have 2 rotations with the same axis but different angles, say you have some Ry alpha and times Ry beta, then that will equal to Ry alpha plus beta. It's pretty easy to check. Maybe I should put that in homework next week. Okay, so homework. Not next week. Next week is midterm, so many weeks later. Anyway, this can be easily checked. Just intuitively, because you rotate on the same axis, then you rotate 2 angles, then 2 angles just adding together. So that's that. And then there's an interesting thing that's nice to remember. That is, if you sandwich some function of sigma y with 2x, then that actually becomes function of negative y. And same for z. And we can see a proof. It's quite interesting and quite quick. So remember that any two polymetrics intercommute with each other. So xy equal to minus yx. This you can just check by definition. Then you multiply x on both sides. Then you have xy equal to minus y. So if sandwich y, sandwich y with 2x, that becomes minus y. And then from here, you can derive what happens. You sandwich a function of y. So we always assume our function is smooth, and it can be written as Taylor expansion because that's how we define, kind of. Because that's just easier. Yeah, and so a function is defined this way. Then we write it in Taylor expansion. So x then is summation an and y to n, and then we can just sandwich we can just put in a lot of x between those y, right? So we think about your yn is n y's here, and then we can just put in x times x between all the y's because you know x squared equals identity. Then you add some parentheses, then all those x, y, x equal to minus y. So this is just an to the minus y to the n. That's f of minus y. Okay? So that's a proof of this. And you can see that if you just replace y with z on the whole proof, it works. So this is actually also true for z. So what we are trying to say is, our b is a rotation on y and another rotation on z. Then you sandwich this with x. That will just, you can once again put 2x between the y rotation and z rotation. Then that will just negate this angle and negate this angle. And now you see that y will pick those funny numbers because we set up everything nicely. Where if you negate b, then everything multiplying together to this rotation z, rotation y, rotation z with beta, gamma, and delta. Okay. So this is just some arithmetic trick where we set up these ABCs that if you just multiplying together, they become notation of no angle. But if you have a times negative angle of b, then times c, then they become your unitary. Okay, so that's our setup. We have this funny decomposition of your any unitary u equal to this ax, bx, c. And why do we want to do this? Is because we want to do arbitrary control unitary u. Okay? And now this is just a circuit. So you have our ABC here, they are single Q unitary, and you have another basically rotation on Z here. So this is 1 e to the I alpha up here, then control X, control X. So why does this work? And I have a typo here, should make a red. Okay. So remember, a times b times c equal to identity. Yeah. So we have set up such that your u equal to e to the I alpha x times b x times c, and a times b times c equal to identity. So if the first qubit is 0, then we don't have those two. Then those two control nodes don't do anything, right? So it's like they don't exist. So the second qubit will just get A times B times C, and that is equal to identity. And obviously you hit here with a 0, then you get this 1, so nothing really happened. So in the end, nothing really happened. Just like here, if the first qubit is 0, nothing should happen. And but if the first qubit is 1, then you have the C times X times B times X times A here. And now this looks a little weird because the order is reversed, but that's just because the order is reversed. The order is different when you are solving equations and solving the circuit. Remember, the time flows from left to right, but when you multiply something, you are basically multiplying from here. So you are applying this C on some side first, then X, then B, then X, then A. Okay. So that ABC is correct thing. Yeah, sorry. This. Okay. Yeah. So anyway, if it is 1, then those control now give you X here. Then you have this AX, BX, C here. And also 1 will hit this E to I alpha here. So the whole thing, so E to I alpha is on the, it seems like it's on the upper qubit, but it really is a global phase. So it's the same. So this is E to I alpha on the upper qubit, same as on the lower qubit. And what happened is you apply this U on the second qubit, basically. Okay, so that's how we do control unitary. Question so far?
Why is that a reference is wrong?
Excuse me? Why is? Excuse me, I don't.
Left to right, and the side refers to why.
Oh, because we think the circuit, the time of the circuit goes from left to right, right? So let's say you have some side here, then your side will get hit by this C first, then get hit by this X, then get hit by this B, then hit by this X, then hit by this A, right? And by you write this U equal to X times B, AX, BX, C here, and you think about what happened, you apply the U on some side. Then this is side here, right? And it's also hitting this side with C first, right? Because when you solve the equation, you solve from right to left. So it's the same order, so C, X, B, X, A. And this is C, X, B, X, A. Yeah. Okay? Yeah. So yeah, that's something to keep track of. It's a bit weird, but that's the notation, conventional notation. Okay, so we have control unitary. Then what if we want more control? Alright, so let's first define what's more control unitary. It's pretty obvious. You can have n control here. So maybe your U is also very big. So maybe your U is on some, say, n bit, and you have n control bit, and we will write it in picture like this. So all those solid data up here, and that just means you apply U here if only if all those things are 1. And you write it in formula, then it's U to this x1 to xn. Okay? So this x1 to xn, it means x1 times x2 times xn. This is a bit ambiguous, but anyway, we probably don't see it too much. Okay, and so that's multi-control unitary, and let's see what can we do if we want multi-control unitary. So first, let's go from 1 to 2. So if we want control U, what can we do? So we want control U. So U control on 2 qubit, and well, then we actually don't use that ABC thing anymore, and here we just give the answer. So the answer is we can do it, and this circuit will work. Well, actually, the ABC thing is useful. So here, basically, we do two things. So first, you need to, yeah, it's a little ambiguous. Maybe I should just do different color. So there is V here. So first, you need to basically take the square root of U. Okay. So this is, sorry for the writing. So, but here's V and here's U. So U is unitary, so you can always find another unitary which square to U. There are actually multiple solutions. And anyway, so if there is this V, then from the ABC thing we just did, we know we can do Control V, right? And also we can do Control X. And anyway, we can do Control V. And so if we place our Control V and Control X in this formation, then you can check it out. So basically, you just check all the possible input up here, right? So 0, 0, 0, 1, 1, 0, and 1, 1. And this will have the same behavior on Control U. Okay. So that's something you can check. Maybe your homework, also homework. There are more homework than I thought here. But anyway, no homework this week. So if we see it, it will be much later. So yeah. Anyway, so that's Control U. And okay, so the counting goes from 1 to 2, then, oh, sorry. Then we can do Control U, and then obviously we can do Control X, right? Because X gate is a single qubit unitary gate. And Control X is the famous Toffoli gate. So that's pretty useful. We can do Toffoli gate. Okay, so we're at 1 and 2, then we are going to do next we are going to say that we can control any Control U. So control to any NU is also possible. But now we need sum and CLAS. Okay. And well, here is the construction. So you have your control qubit, and let's say n equal to 4 here, so 1, 2, 3, 4. And we will need to do sum and CLAS here. So this construction is actually much easier, much more intuitive and easier to check. So what you are doing is you just adding, not quite adding, I guess multiplying all the input on the control qubit up here. So you are checking where is 1 is both C1 and C2 equal to 1. If so, then you write the answer down with your Toffoli onto your fancy and CLAS. Okay. So I forgot to write here, but the CLAS are all initialized with 0 here. Okay. And they will be returned to 0 after the computation. Okay. Okay. Yeah, so here what we do is we check is C1 and C2 both 1. If so, then you write 1 here. Then you check is C3 also equal to 1. If so, then this Toffoli will write 1 here. And then you check is C4 also equal to 1. And if so, you write 1 here. Then you just do your one control unitary here. And as we said, the value here will be C1 times C2 times C3 times C4, right? Because this is 1 only if all of them are 1. And after this, we are not quite done because heavy and CLAS in this weird state. This up to here, the ancilla can actually have some entanglement with all other things, and that will actually make your computation not quite right. So what we need to do here is we need to uncompute everything on ancilla. So yeah, so we uncompute everything. So we once again integrate this C4 and this thing and this and this. So you are compute everything to ancilla. So they will return to 0, 0, 0, whatever your control qubit and the target qubit is. Okay, think about this, and yeah, it should be easy to see that whatever your input are control and target are, even if your control and target are entangled, if you do this on compute, your ancilla should return to 0, 0, 0. Okay. And then your control and the target will really yeah, so these ancillas are input with 0, 0, 0 and end up with 0, 0, 0. And what this whole thing is really equivalent to full control of the U on your target qubit. Okay. Any question? Okay. So we are pretty good on our schedule. So now we have arbitrary controlled single qubit unitary. And that's pretty cool. Yeah. So once again, arbitrary control. Okay, so this is multi-qubit, but actually only need single qubit for here. We have arbitrary control single qubit unitary. Then we have our roadmap for our Cornell University once again. And so the end goal here is we are trying to show that HEDMA, T, and C0, only those three gates is universal for any quantum circuit, and that's approximately. So we are doing this in 3 steps, and the first step we actually haven't seen. So the first step is we are going to decompose unitary decompose our circuit into unitaries on two computational bases. And so this thing is actually the thing we just showed. This is basically multi-controlled single qubit unitary. Because if you think about the droid here, right? So we have the thing up here equal to, okay, let's keep the same number. So 1, 2, 3, 4, right? We think about this gate, U here. And we think about the matrix here. And what will be the matrix? It will be, actually, so confused. It will be identity, and so there will be a single qubit unitary up to the corner, maybe not this corner. It will be this U down this corner, right? Is single qubit unitary, so it's 2 by 2. And so this is when everything is 0, 0. Everything is 1. So all other qubit is 1. There is 1, 1, 1, 1. and 0, 1, 1, 1, 1, 1, and 1, 1, 1, 1, 0, 1, 1, 1, 1, 1. And it should be 0 up here, and okay, yeah, and identity on all other place, right? And this is the kind of thing we call two-level unitary. Although it's more general, then we are going to shift this unitary around. Okay. It's two-level because it's one level, two level, one level, two level. Okay. Okay. But anyway, we're first going to decompose everything to something similar to this, so multi-control single qubit, and then we are going to show that those two-level things can be decomposed to single qubit unitary U and C naught. So we already see some of this, say here, right? Here we already see those toughly can be done with C naught and single qubit unitary, because toughly is one of those, and this is done with C naught and control unitary, and control unitary is also done by C naught and single qubit unitary, right? And so toughly can be done with C naught and the single qubit unitary, and as we said, this control unitary can also be done with C naught and 1 qubit unitary. So everything up here can be done with C naught and 1 qubit unitary. And this is also exact. And then the final step, which is also called Solovay-Kitaev theorem, is say that this arbitrary single qubit unitary can actually be done with also only Hedema and T-gate. And this is now an approximation. Okay, question so far. It's probably not too clear because this is a very rough sketch. But now let's see what happened. Okay, so two-level unitary. So we are trying to decompose any unitary U. So any this 2 to n times 2 to n unitary. So thinking we're on n qubit. So the 2 to n times 2 to n qubit unitary, 2 to n times 2 to n dimensional unitary into two-level unitary. And so two-level unitary, as we said, is a unitary that are almost identity everywhere. So you have a whole bunch of 1 on the diagonal and 0 everywhere, except there are two levels. Okay, so there are two levels. So you pick 2 columns and 2 rows, and those 4 places will be some 2 by 2 unitary. So okay, so it's like this, and we are saying you can multiply a whole bunch of unitary that look like this, and get arbitrary unitary to the 4 square. And so here let's not say 2 to n because we are giving a example that's not power of 2. Let's say big N times big N. And so here is an example. And we won't go into too much detail, but you can assume, say, your unitary is 3 by 3. And so you say the entries are A, B, C, D, E, F, G, H, I, not I, G, H, J. And then you can try to decompose it into some two-level unitary. Let's say U1 times U2 times U3. And what you do is you find first you find the U1 such that when you multiply the U1 on your U, then this entry becomes 0. Right. Remember, you have a 4 3x3 thing. Then you have your U1 looking at this is something between your first two, and you set up the number so that this entry becomes 0, and then you do similar thing. You set up your U2, and there will be these two levels. So this 1, 2, 3, 4, and you will make this entry equal to 0, and oh sorry, wrong. And so that's the U2, but there is some detail. But so you multiply your U2 on your U, then you will make this entry equal to 0. But because this is 3 unitary matrix multiplying together, so it's still a unitary matrix. And so this is 1, then those two entry must be 0, because this column must be normalized. So actually you get this thing. And then now this is another 2-level unitary, and you see that your U3 will equal to this, the inverse of this remaining U prime. And so you see that you can decompose your U equal to this, basically this U1 times U2 times U3, although you want to write it in different way. So you see those multiplying into identity. So your U actually equal to U3 dagger times U2 dagger times U1 dagger. Okay, this is a quite basic explanation, but any question? We skip the detail of the formula, but you can probably feel that because you have lots of freedom to construct your U1, U2, U3. So it's not too hard to make the product of it with your U to have an entry of 0 somewhere, and etc. So what happens of you applying this U1 is basically you do some linear combination on those two. Is it? I think so. Yeah. Basically do some linear combination between those two rows, and you set up the linear combination such that this is 0. Then you do a linear combination between those two rows, and it can make this entry 0. And then just by this matrix is still unitary, then this is 1, then this row is normalized, so those must be 0. And then you see this is block diagonal now. And by the property that this is unitary, then this color and this color must be also normal to each other. So this 4x4 part is actually a non-unitary. And so you can find the inverse of it, and this is also a unitary. Question? No? Okay. And huh? Excuse me? Square. Oh, you mean why is this empty? Because I'm just lazy. so the square root is the same of all of them. So yeah, so the empty thing should be the same. Yeah, and I'm not sure. I forgot. Maybe the textbook has all of them, but maybe they don't even write this. I don't quite remember. Yeah, so for U1 you have the same, and for U2 those are also the same. And that's that. And then you can see that. So this is an example for 3x3, and you can probably already feel that This is actually possible for any what's the number we use here? Any d by d matrix. And we do this by induction. So let's say we can do this for any d minus 1 by d minus 1 matrix. Then you have d by d matrix. Then you can do some operation and make it is 1 0 0 and 1 0 0 0 0 thing by multiplying. And actually I have the wrong ordering, right? Anyway, it should be then say NDD can find U1 to UD minus 1, so it should be okay. So it should be 1 here. So UD minus 1, UD minus 2, and a U1 here. Yeah, anyway, you can find D minus 1 matrices because there are D minus 1, 0 here. And you multiplying, then on your U, you make it all this 0. And that will also force all those 3 0. Then you get a D minus 1 by D minus 1 matrix here. And you know this can also be decomposed into a whole bunch of two-level unitary. So you see that you can always do this decomposition. And okay. And then you can count the number a little bit. Then you find out that, so if your D equal to 2 to the n, so you are doing n cubic unitary, then the number of two levels you need to use is about 2 to the n squared. And the detailed number is this. And it's probably not too hard to count, so the number you need to use is this, where you're adding 1, 2, 3 to up to d minus 1, so the total number is 2 d times d minus 1 over 2. And so anyway, that's like yeah. So if you put d equal to 2 to n, that should be equal to this. Okay, so that's decomposing. Okay, we still got some time. Anyway, question yet? So that's decomposing any unitary to this a bit weird two-level unitary. And just as we said in spoiler, we are setting up those two-level. We are doing it into those two-level unitary because it can be done with multi-controlled single qubit unitary. And okay, now it's quite a bit of confusing part. So we are saying single qubit unitary plus CNOT is universal. And first we are decomposing our arbitrary circuit into two-level unitary. And now we are show how to do the two-level unitary into CNOT and a single qubit unitary. Okay. And the idea really is you want to change your two-level unitary into multi-control single qubit unitary. Yeah. And so remember you were so we feel that our two-level unitary or Bermuda is the dimensions here, such that this ST is, well, it can be placed last or first. But let's say we place it on the first two dimensions. Okay? And as we said, this is really a multi-level, multi-control unitary, right? So this thing is, well, because we place it on the first. So this thing is really just your multi-control with this empty control. So control on all 0 and your qubit. Okay, so that's this thing. Okay, and so if we are applying this, we know how to apply this thing. This is multi-control single qubit unitary, and as we said, it can be done with CNOT and single qubit unitary. And how do we switch from this to this? So there are a little more detail, but this is basically some arithmetic. This 3-qubit example is toughly, but we are just going to do a whole bunch of multi-control NOT, although some of the control will be control on 0, some of the control will be control on 1. And so here is an example of we are constructing this U that's 2 level on 3-qubit thing. So you have A, B, C, D on here, and so you want to swap this 0, 0, 0 to you want to swap those A, C, B to like here, right? And what's our it's a little annoying. Anyway, so you want to move those to like here, A, C, B, and and when that happens, and it will be like this control U, and to swap those around, then you basically need to do those multi-qubit control NOT, but sometimes you are control on 0, and sometimes you are control on 1. And so really the 2 paragraph here is trying to argue that the moving an S and T around is possible. So it's possible to move any ST and push your 2 level into a single qubit. And you can read those, it's not too hard. So basically, yeah. It's a little more complicated because sometimes you don't push them to the whole angle. Sometimes this is a little more optimized because sometimes you will push your ST to maybe not the first or second. So here we are pushing them to the first qubit, and maybe you will sometimes push them in the middle because that's easier. Anyway, I hope you are convinced that it's possible to swap around, and here we give a very quick showing where you have S and T written in bit string, and so you actually want them to be differed by only one place because that happens when they are on the same qubit. And so you just look up the locations of how many different locations of those 2 strings are different, and you set up a sequence such that you change the difference one by one. And so going back and forth going back and forth on those sequences require a whole bunch of multi-control NOT. So you want to swap between G1 and G2, say. Then you want to control on those 4 things. Those 5 things are actually 1, 0, 1, 0, and you flip this bit. Then you will swap between G and G1, and you will swap G1 and G2. Then similar thing. Then there are similar things, so you want to swap between G2 and G3. Then you control on those things being what they are, and then you flip those 2, and etc. So that's what those generalized toughly will do, or multi-control X-gate will do. And anyway, you will swap the S and T into being close to each other, and you apply your multi-control unitary. So hopefully you are convinced, and we are just on time. So any question? Otherwise, let's have a break. Okay, let's take a break. Resume in 10 minutes.也不是吧，我想想看，如果不玩 computer 的话，
这样那些 N 型啊，可是到时候会丢掉。
等一下，你在说的是你是说前面的那个吗？你是说那个 Ctrl U 的吗？那个会坏掉。你说这个？
对，我想说这个会丢掉。
对，可是你不玩 computer 的话，它会跟其他都是 entangle， 所以你丢掉的时候其实会出问题。我想想看这是怎么给例子的。
entangle 是后面 measurement 会出问题。
就是后面 state 的会 decode here。我想想看这个要怎么给。就假设，OK， 就假设其实什么都不做吧。这个是一个。我们其实什么都不做。我们这里有一个正的 state， 然后这里有一个 C 大是零的，然后我就做了一个 C 大的这样子。应该说这个是给我们算过。对，然后它会变什么？问题。0.1加1，对不对？那这个东西在第一个 circuit 上面是什么？这样的话，在第一个 qubit 上面，我们用 reduced matrix， 然后这样的话就1好了，会等于1/2的一个东西嘛，对不对？因为我们就把这丢掉，所以我们只看就1在这里，对吧？但是我们知道，如果是没有做这个 C 大的时候，正是等于1/2的两个其实不同的东西。但是如果你把它 uncompute 掉的话，那这个对，可能是正比。然后这个的话 uncompute 掉，那这里又会变成这里了，对吧？这个 uncompute 是需要的。那个其实跟那个 deferred measurement 有点像嘛。因为如果不让它 Q 掉的话，这个其实就像是你在这里做一个 measurement 把 measure 掉的感觉。 然后那我们知道，这个 matrix 对 ABCD 好了，这个 matrix 是 unitary if only if 它的那个 column 是 orthonormal 的嘛？那这里因为都是零嘛，那你 check 这两个是 orthonormal 的话，跟这个是 orthonormal 是一样的，因为这上面是零，所以这整个弄完就等于这里弄完，然后这个整个弄完等于这里弄完，然后这样 inner product 等于零，就是等于这样 inner product 等于。
这整个是
从它其实还是个 unitary 来的，我们要这个东西是个 unitary 嘛，它是个 two level unitary。
这个应该会是在规东西上面。
对啊，弄回来，这个是其中一个，这个是某个 UI 这样的。我们说每个 UI 都是 two level unitary，所以这个是 U1 还是 U2 之类的。
这是上面有写过漏的时候，
哦，那个讲义吗？哦，因为我把有些东西混在一起讲，对吧？像这里的话，应该说 U3 吧，这个有点像 U3 这样。
这个步骤前面看起来像在做高斯小区法。
对啊，有点像，但不完全是。
对，感觉这里就是做成高斯小区法做列操作什么的，
对啊，有点像，不太一样。我们有限制它是用特率就是了，但是的确有点像，需要的步骤那也是一样的。
对啊，这样是这个东西是 U2 U1 U2。这个是什么变来着？就是把底下这拿去把它消掉。
没有，这里是说，因为这里都是零，所以这要是一嘛。那这里是一的话，那这一个列它的弄要是一的话，那这两个数字就只能是零，因为这里已经是一了，那这里就没有任何的weight可以放。因为整个列这个肉的弄是一嘛，那这一平方加 d 平方加，然后这两个弄平方，这已经一了，那这两个就只能加零上来。
所以前面不是在做，所以这样好像也不是高斯小区，
对吧？不太像，其实不一样，但是有点像。
那现在这个 U1 U2 都是 unitary，
都是 two level unitary。
two level unitary。
因为我们画的 U1 是这样子嘛，一个 label 两个 label， 虽然现在总共只有3个 label， 所以有点那个有点奇怪。但是这里第一个 label， 第二个 label， 这里一个440。
那个 label 是什么？two
label
label
是有点像是两个肉两个 column 啊。
那如果 three label 就会变3个。
但是我没有用 three label， 就是 two label 就是只有这个2×2的地方是比较特殊的，然后其他地方是 identity 这样子。就是想象它是有点像是这个 unitary 会是，应该说，你想象把这个移一下的话，它会像最后这种感觉吗？应该说，应该说我之前画的还在不在？对吧？像这种感觉吗？就是这里这样子两个 label， 它们之间有一个 unitary 在转，然后其他地方全部都 identity 这样子。所以叫 two level unitary。label 是有点像就是 dimension 的感觉吧？
是指这个 U 的 dimension。
对啊。
所以如果现在 U 是4×4，那它就会是 four label。
对啊，这样子命名算是合理的，虽然我们没有用到，我们是用到 two label 的。
那后面不是有一个 U 是2乘2？
没有吧？哪里有2乘2呢？
不是2乘，给那个3乘3，所以那个就变
3乘3，哎，等一下，我卷过头了吗？你在说的是哪里？好像
可是后面本来不是要写2的n4方乘2的n4方？
哦，那个是
例子是3乘3的那个。
OK， 你是说3乘3我们来猜的这个例子吗？对吧？一开始的这个没有，这个是你的 quantum circuit， 这个不是 two level 的，这个就是任意的 unitary。我要把它写成一堆 two level 乘起来，所以 U 是 arbitrary， 然后 U1、U2、U3 都是 two level 的。
就是前面一堆1，然后后面 U 是2乘2。
对啊，虽然说它没有啦，这里是比较 general， 我们没有说它一定要放在最后面。我们说这个2乘2你可以放在任意的2个 level 这样子。对吧？就是任意的2个 dimension。
是指这个是 U 的那个 A、B、C、D。对，
让你看到吗？
我以为这是那个什么矩阵，把它切割成4块。
没有 ，OK， 这个不太清楚。
所以是这个东西是 A、B、C、D。
对，我这里应该要写，对，这样子就懂了。OK， any question? Okay. Seems like there's a little confusion on the two-level unitary. So once again, so two-level unitary is like a block diagonal matrix. So it's this identity everywhere. So it's diagonal being 1 everywhere and a 0 everywhere, except there are 2 dimensions. So some dimension, let's say, S and T here. And when you restrict to S and T, there is a unitary, and those 4 dots are actually the 4 component unitary. So let's say you have A, B, C, D here, and you think there is some U star equal to A, B, C, D. Okay, hope that's clear. So that's so there is a 2 by 2 unitary embedded into those D by D matrix. Okay, hopefully this is clear. And anyway, so we show any unitary can be decomposed into 2-level unitaries. So like this, so you see you have A, B, C, D here basically. And we show you multiply a whole bunch of 2-level unitary together, you can get any unitary. And we say any 2-level unitary can be decomposed into C0 and single qubit unitary, because you can do those kind of things. You can do multi-control knot to shift your 2 levels around, and that's 2-level unitary. So actually we use U tilde, so let's say U tilde up here too. So as we said, where is it? As we said, the 2-level thing is like a U tilde here, and so you shift them around such that this 2-level is actually on the same qubit, so it's like a multi-control unitary, multi-control U0. And for details, you can look up the discussion on gray code and the things. And there is also a nice write-up of this in the textbook. Okay, so people buy this? If so, then let's continue. And we are pretty good then. Yeah, and as we said, so we proved that those multi-control unitary and the multi-control C0, multi-control X gate can be done with C9 and a single qubit unitary. So we showed that very cool thing that So we already showed that any quantum circuit can be done with the CNOT and a single qubit unitary. So that's our first universality class. And you can do a bit of counting about how many gates you need to use to construct your quantum circuit. And so each control U is about 1 gate, etc. And at the end, you see that you need about this n squared times 2 to the 2 n gate. It's quite a lot because it's exponential in this n and quite a big exponential. But anyway, we are only showing that this is possible. Might not be too efficient, but it's possible. And I think the book might have counting lower bound on this, and I think it might be tight. I don't remember right now, but there are actually a lot of unitary possible in 2 to n times 2 to n dimensional space, so this might be tight. Anyway, it's a lot of gates. Question? If not, then let's go into, okay. Oh, we are pretty fast. Okay. Okay, then let's go to the other part. So now we know our, let's just write it once again. So now we know the roadmap is, we know C0 plus single qubit. Unitary is universal. And as we said multiple times, we are going to show that you can decompose this single qubit unitary into just headbar and T. And the short version of this is you can look up the paper, Solovay-Kitaev, famous work, and say you can do this in order log to some constant C and 1 over epsilon gate. Very efficient. And well, then here we get the poor man's version of Solovay-Kitaev. And so first we talk a little bit about what is this epsilon here. So we say epsilon is error, but what do you mean by an error on a unitary? And well, to define an error on a unitary, first you need to define distance between unitary matrices. And there are a lot of definitions that make sense. And here we use one of the most popular one, that is the spectral norm, and it's defined this way. So it's a norm on unitary. So it's a norm on matrices, and well, if you have a norm, then you can define distance because you just put a norm on the difference between your two matrices, right? The distance on your two matrices. So this is the distance between your two matrices. And anyway, so the spectral norm is defined by basically the largest eigenvalue, but also actually largest singular value. But here we write in a bit more operational way. So we say it's maximizing is a maximum of those values. So you see the difference, and you apply it on any vector with length 1, and you see how large that vector becomes. Okay? And this is basically the largest singular value, right? If you think about the singular value transformation, singular value decomposition on this part, and this will be largest singular value or largest absolute value of the eigenvalues. Okay, largest singular value. And anyway, So that's the norm we use, spectral norm. And it has nice qualities. So first it's norm, and so as usual it should satisfy triangle inequality, and also it's very nice. It has unitary invariant. That means if you say you apply a unitary U on your some matrix A, then that's actually equal to norm A. And if you apply unitary after your A and then do your norm, I think that's also equal to your A. Yeah. So it has lots of symmetry and do the thing we expected, etc. And obviously it's bigger than 0. And and also the quality you expect from a norm. So the norm difference between two matrices is 0 if only if your matrix or those two are actually the same, etc. So question. Anyway, that's a special norm. And okay, and we didn't say here, but so the epsilon here is defined by the spectral norm. So it's like if you want, so there is some u want to do, and there is some u tilde you construct from your Hedema and the T, and you want the distance or the spectral norm between them to be less than epsilon, and then you need many gates. Okay, and so that's the area we want to do, but and now let's switch to the idea of how we actually get everything from Hedema and the T. So our poor man's version is now we need to think our block sphere once again. Block sphere is very useful because now we are focusing on single cubic gate. And first we define a new family of gates that's rotation with angle theta along some direction n in your block sphere. Okay? And clearly you can clearly see that this is the generalization of our rotation along sigma x or sigma y or sigma z. Right? And so that's a so say this n is 100, then you will have this n dot sigma equal to so sigma 1 is actually x, right? X, y, z. Okay. So yeah. So our rotation on x, y, z is just choosing this n hat in x, y, z direction. But now we are saying we can have this in arbitrary direction. And so we didn't give proof, but they will actually correspond to rotation on block sphere because of some physics reasons. And okay, so let's have this mental picture of rotation on block sphere. And now we think about what kind of rotation we can get by piecing together all the Hedema and the T. And so first thing we will do is we do this sequence. So Hedema, or maybe from this direction, so T, then Hedema, then T, then Hedema. And it will be some rotation, some direction, and some angle. Yeah. and and we are really doing this in clearly is that theta divided by 2 pi is irrational. So theta is the irrational multiplication of 2 pi. That's a important thing here. Okay, so theta divided by 2 pi is irrational. And then why is this important? That means you can repeat this thing, and now we need to remember your calculus. I believe. Do you teach about irrational number in calculus? Actually, what? But hopefully you learn about irrational number somewhere, and and the property is that so if you keep multiplying this irrational number, right? So you keep doing this ht and ht, and we say it's a rotation, so the angle will just add up. And because this is an irrational number, so those k theta is never going to repeat itself, right? Because, well, that's the definition of irrational number. And so any k theta will never equal to multiple of 2 pi. And actually it will be dense between these. If you have this mod 2 pi, and also from the property of irrational number, you can prove that this rotation will be dense every possible this interval between 0 and 2 pi. And that means that if you keep doing this, then you can approximate any angle alpha along this n-axis. Okay. Hopefully people still remember this calculus about irrational number. Yeah. So we just repeat ht probably many times, and you can get an approximation to any rotation along this n direction, because theta is irrational. Okay, and then we get rotation on another angle by sandwiching this Rn theta with gamma. You can also show that, and yeah, so you sandwich this Rn theta with gamma. So I believe this thing is actually th. But anyway, you do this, and that will be the same rotation angle theta. But what's important now is you will be a rotation on a different axis m, different direction m. Okay, m not equal to n. And now, as we said, this theta is irrational. So you repeat this enough times, then you can get rotation on any angle. Let's say beta here, right? And arbitrary angle beta along this m-axis. Okay. So we have set up quite a bit and argue that we can get rotation along this n-axis and rotation along this m-axis for arbitrary angle alpha and beta. And then we are done, although there is a bit of correction we need to do here. So let's draw picture, and okay, let's draw again. So we have our block sphere, and there is some direction head and some direction m head here. And so you can do arbitrary rotation on this and arbitrary rotation on this. And here we claim that because you can do those. Then you can piece them together enough, and you can do. So you just interleave between rotation on those two axes with some angle set up good. Then you can actually do arbitrary rotation on the whole sphere. Okay, so that complete a proof, except there is a little correction we want to do on the book. So you read Nielsen and Tron, it says you can do this just like what we do in the ZY decomposition. So you only need three rotations. Right? We say if you have a rotation on z-axis, a rotation on y-axis, and a rotation on z-axis, then you can tune this alpha, beta, gamma, and delta, and get arbitrary unitary. Obviously, also with this phase e to the alpha. And this is actually not true because this is only true. This kind of decomposition is only true because y and z here are orthogonal. And so for this n and m, you think if we consider extreme example, and say those two vectors are very close to each other, right? And you think about three rotation around them, then it's very similar to just the rotation on this general thing. And yeah, three rotation on them is not going to give you any rotation. And so this is not correct, but so this is not correct in that you need to do more than three of those rotations to get everything. And it actually depends on the angle here. Right? There's the angle, what other letter we are left with? Let's say alpha, beta, gamma, delta. Let's say the angle gamma here. Let's say the angle is gamma here. Yeah. So the smaller angle gamma here, the longer the sequence you need to get. So you see the y and the z is the base case because they are totally orthogonal to each other. And and so the length of the sequence is about 1 over gamma. You can look it up. But anyway, but really there's nothing scaling here because Hedman and T is unfixing. So the angle gamma here is constant here, and so yeah. Yeah. So the angle is gamma here, and the length of the sequence. Is about 1 over gamma. Gamma is a constant, so the length is some constant. And you can do any rotation. You just need a bit longer sequence than this y and z rotation. And we skip a lot of detail, but if you want to analyze the number of gates used in this poor man's Solovay-Kitaev, and you will find that we need to use omega 1 over epsilon gate. So that's worse than what we claim as possible. Once again, remember Solovay-Kitaev have polylog 1 over epsilon. So it's exponential worse in error, but suffice to show that this is possible. We are getting this 1 over epsilon because we are being pretty dumb on how to approximate our rotation here. We need to do this irrational number approximation of anything. Okay. And anyway, We are in a weird spot. Any question now? Our poor man's solar kickoff, where we do rotation on this direction and rotation on this direction. Yeah. No. Then that will be all for our quantum universality. And we have 20 minutes more. Let's talk about something. Let's see. Maybe I can finish that. Okay, then let's talk about this new content. Okay. And so we have this small note on computer science tool and concepts that will be useful for later part of the course. And so the first thing we want to talk about is probability. And actually I'm kind of curious how necessary are those things. So how many of you actually heard about central limit theorem? Raise your hand. No? Seriously? How many of you heard about Chernoff bounds? No? You hear about it. Okay. Okay, anyway. So those are concepts that hopefully you hear somewhere, but hopefully you heard somewhere, but too shy to raise your hand. So you can average it into some axis. But anyway, you average your random variable, and your random variable might have some weird distribution. But you average a large number of them, then the average will have a distribution that look like Gaussian. Right? So you will look like this, and look like Gaussian, and the middle part will be so the middle part will be obviously the average of your random variable, and there will be some standard deviation, that's how sick your Gaussian is, and more importantly there will be some exponential tail of your Gaussian. Right? And we say independent random variables, so, but really most of the time, let's say you think about coin toss or you do some experiment, right? So you do some experiment, and there is an expectation value, and what you want is you do your experiment enough number of times, then you want your empirical value to be close to this expected number, and you say a few standard deviation where you have an exponential tail. Okay. Yeah. So let's say something we expect is you do coin-toss. If you have a fair coins, then the number of heads should be about 1/2 number of toss, right? That's the thing we expect, and the probability that you have a larger deviation from this should be exponential suppressed. And okay, so that's the intuition question so far. Yeah, and so that's the expectation, and now we want to say these things more formally, and we'll introduce two inequality. So Hofding and Chernoff. Okay. So let's set up things a bit more formally. So our independent variable, we call x1 to xn. Okay. And then we have some sum over them. So I have a random variable x, that's sum of a whole bunch of n, small n independent random variable. So xi independent. So x1 to xn. and then we write. Then this is just notation. So this mu is the expectation value of x. So it should be the true average of x, big X. So first bound is Hofting. And so we need extra condition. So we need to have those random variable have the bounded range. So let's say every xi has the lower bound ai and the bi, upper bound bi. And this means that there is no probability that it will be smaller than ai, and no probability it will be bigger than bi. And then we have two bounds. We can bound these two sides. So we say this sum cannot be much larger than average. So the probability that it's larger than this average plus some number t, or the probability that is smaller than average minus some number t is less than. So you can look up in Wikipedia. It's a little confusing, but I believe this is a true formula. It's less than 2 times exp and minus 2. 2 times t squared, so t is this t. So you see this is like exponential suppressed by this t here, right? And divide by, and you have something like standard deviation here. So divide by things is actually this bi minus ai and square, then sum over oi. Okay. And this is true for all t bigger than 0. Okay. And let's see an example. So our coin toss. And so let's say our x1 to xn coin toss. So let's say it's fair coins, independent fair coins with probability 50-50 being head tail. And let's say head equal to 1 and tail equal to 0, right? And so then what's the probability of a pretty large deviation? Let's say if you have n toes, so you expect it that 1/2 of the toes will be head. And let's see, you say what's the probability you have a pretty big deviation. So you have 3/4 n times 3/4 n of them being heads. Okay. And then you use this formula, right? So now your x is the total number of heads. Okay. Number of heads. And then the average should be 1/2, sorry, n/2. And the deviation here is this 3/4 minus 1/2, so 1/4n. And then what is ai and bi? Well, you only have, so your coin toss only have two results, so head and tail, corresponding to 0 and 1. Sorry, 1 and 0. And yeah, so 1 and 0 are obviously bounded between 0 and 1. And then we put into this formula. So yeah, so probability x bigger than mu plus 1/4n is less than 2 times the exponential, then everything, so minus 2, and t squared is 1/4n squared. Then summation bi minus ai is just 1 minus 0 squared is still 1. And so you are summing over n once, so this is just n here, and you do everything. Then you see that the probability is bounded by 2 times the exponential minus n/8. So this is quite what we expected. So this is exponentially suppressed with this n here. So as you toss your coin more and more times, the probability that you see this kind of deviation is exponentially separated. Okay, and if you can have so why would we want to talk about this? So we can think about let's say an algorithm. This can be very useful for amplification, right? So let's say can we do this? Probably yes. So we have algorithm success with probability 2/3, right? And then let's say algorithm A. Then you run A like 10 times. Then okay, it's a little it's more complicated. Okay, it's more complicated to write it here, so that's not write in detail, but a thing also possible is that you have algorithm A solving decision problem. With 2/3 probability, and then you can, let's say, run A 10 times, and do majority voting. Then you can see what's now the 2/3 amplified into something, and that should also get this kind of exponential tail. We don't have the space and the time for this right now, but so let's see another bond that's actually more famous. It's called channel bond. So it's very similar to Huffington bond, except that we have basically multiplicative error here. So the setup looks a little different. So here we have that every xi is bounded between 0 and 1, but this can be easily deal with. So if your xi is not in this range, then you want to scale into some other random variable with this bound. Okay. So every xi is between 0 and 1, and now you have some multiplicative error epsilon bigger than 0, and but now we don't have one simple formula. So the formula have two sides, and if you look at Wikipedia, there are more of them, but I believe those two are the most useful one. So if your x is less than your mu, but far away with some multiplicative error 1 minus epsilon, and so this probability. So this is basically tail. This is basically on the lower end tail, and this probability is exponential suppressed by will depend on this epsilon. So minus epsilon squared over 2, and then times your mu. And on the other side, if your x is bigger, so basically this tail on this part, so your probability x bigger than 1 plus epsilon mu is also exponential suppressed, but there is a little difference, and it's actually necessary. So it's epsilon squared over 2 plus epsilon. times mu. And so if your epsilon is very small, then this plus epsilon doesn't matter, but this is true for every epsilon. So in case you want some very large epsilon, then you need to remember this formula. And also, if you really don't want to write this, and suddenly 2 and 3 doesn't matter, then you can have this less than epsilon squared over 3 mu. This is true for epsilon less than 1. Okay, and yeah, so this is a famous Chernow bond, and you can use them to bound a lot of probabilities. Mostly when you amplify things, like the example of you amplify the success probability of your algorithm. And we can run this through the coin flip example also. So also we have fair coin, and we want to see what's the probability you got 3 over 4 over the heads. So here the mu is still 1 over 2, right? And the epsilon now is 1 over 2, right? Because you want this whole thing to be 4 over 3. 3 over 4. So yeah, that's 50% more than 1 over 2. And yeah, so you plug in the number. So mu equal to 1 over 2, and epsilon equal to 1 over 2. And we need to use this formula, and we get this. And you clear everything up, and you see this exponential minus n over 20. So it's still exponential in n, but it's a bit less tight than this. So that's a bit annoying, but usually we don't care about this number too much. We want to know is exponential in this n. For string so far. And okay, so some comments on Chernow bond. So when is the Chernow bond being more useful than Helfting bond? As we see, it's actually worse than in this example. So I think the most difference is this is really a multiplicative error here. And so this will give you better bond when your mu is very small. Okay, so let's say if your mu is also scaling with n, then you get some extra scaling with n here. So that will be nice. Yeah. And also a little thing to note here is that although this is not quite proven here, so we need to take my word. That is, you can use Chernow bond a bit more leisurely when you don't know the mu exactly. So if you don't know mu, but you only know a bound on mu, okay? And so you know mu has some upper bound mu h, then this thing is actually true. So you can replace everything with mu h here. So this is not black box obvious from here, because although this probability will be smaller than this probability, then this number is actually not bigger than this number, because you are super small. But anyway, this is true. So you can use this Chernow bond a little more leisurely. Okay. And oh, we have 5 more minutes. And can we finish this? It's a little longer. Okay, let's try to finish this. And the other thing I want to say about in this computer science note are graphs. Okay. So I mentioned this very briefly before, but let's say this again. So when we talk about graphs in this course, it means a set of vertices and a set of edges. Okay. So it's something like this. So I have some vertex 1, 2, 3, 4 here, and some of them will be connected by edge. So edge always connect two vertices. Okay. And yeah, so we'll write something like this. So you have some graph G, and that is described by the set of vertex V and the set of edges E. And if you know about these mathematical graphs, there are more modifications like basically on the edges. So sometimes the edges can have direction or weight, but here we consider the simplest example. So the edges is just something that connect two vertices, and so there is no direction and no weight on the edge. Okay. So this is graph that we think about. And yeah, so computer science. And the important thing is how you access the data. So you have something here, and in this course, so you need to access these vertex and these edges, right? And the vertex, usually we have very easy access. So they are labeled with just string of numbers. So usually it's just 1 to 1. So it's easy to find the vertices. And maybe there are something special, maybe 0, but usually it's just 1 to 1, and there are n vertices. Okay? So you can just say vertex 1 is 1, etc. And then the edges are more special. So you know the vertices are just those numbers, and now you need to ask whether those you need to find the edges, right? And there are two models. The first one, I think it's more natural, but anyway, so it's the density matrix model, and what it does is you want to check whether two vertices are connected. Okay, so usually you do this with the oracle. So there's an oracle, you can input some vertex label, two vertex label I and j, and so you ask the oracle I and j are they connected, and the oracle will tell you yes and no. And it's called the density matrix because you can put out all the answers with the matrix. And so row and column labeled by 1, 2, 3 to n, 1, 2, 3 to n, and there is 0 and 1 tells you that whether two things are connected or not. Right? So for example here you can ask is 1 and 3 connected, and it's not. You can ask is 2 and 3 connected, and it's yes. And so that's a density matrix model, and there's another model that's called a density list. This is okay. Yeah. And yeah, so this is also things people consider. So instead of asking whether two vertices are listed, this model, the oracle is, I guess, a bit smarter. You basically ask what are the neighbors of your some vertices, and actually it will give you order of the neighbors. So let's say you will ask, I want to look at the vertex 3, and what is first neighbor, and there should be some ordering. Let's say you just go with alphabetical order, and so you ask what's the first neighbor of vertex 3, and the oracle will tell you that it's vertex 2, right? Because here. And what the second neighbor will be vertex 4. And what's the third neighbor, it should tell you there is no third neighbor. Okay. So that's the density list model. And we are just on time. So let's stop here for now. And any question? Otherwise, we'll have a midterm review next Monday, and we'll have a midterm next Thursday. Okay? Okay. See you next week.